Hi, my name is Stuart, and this is the third in a series of Azure videos. Today we tackle the subject of queues. So queue mediation is probably one of the most powerful enterprise patterns, and as such it's often used in cloud projects. The essentials of it is that we want to decouple producers from consumers so that either the producer or the consumer can be offline and we won't have any loss of data or messages. And what makes enterprise queues special is that they have very long message retention, typically on the order of days or even longer, are very high scale. In other words, producers can pepper queues, enterprise queues, with messages without loss, and are fundamentally lossless. In other words, almost nothing would cause a message once it is ensorcelled into the queue to be lost, other than someone programmatically consuming the message and not doing anything with it. But once the message is in the queue, the chances it will be lost are remote. So here's the fundamental queue pattern. They're first in, first out under extreme conditions. And what is interesting about that is, depending on the queue's configuration, the queue can serve up messages to multiple consumers in one of two ways. They can either serve the message to consumers in a sort of a round robin or first come, first serve basis. In other words, multiple consumers can get messages from an enterprise queue, and those messages are processed by each of the consumers separately, and so no message gets processed twice. The other methodology that queues can have is that queues, as we'll see later, have the ability to deliver the same message to multiple different consumers, and that's a useful and special case. The third thing to consider is queues can be made to have absolute message order processing or only approximate message order processing. And by that, we mean that just because consumer A picks up the first message in the queue and consumer B picks up the second message and consumer C picks up the third message and so on, consumer C could conceivably finish processing the message before consumer A did, depending on the complexity of the message and the complexity of the processing. If the desire is to have strict in-order processing by the consumer, this is a property that you can set on the queue, and it will, however, have the side effect of dramatically throttling the ability of consumers to consume the message queue, and is almost always unnecessary. In other words, whether or not message A or message B processes and finishes first, in most scenarios it simply doesn't matter. There are a very few scenarios, such as auctions and trades, in which strict message processing order is important, but there are a number of ways of getting the same result without configuring your queue to necessarily only offer up messages in order to consumers. The other thing is that message queues are generally classless messages. In other words, anything can be the payload: byte array, XML, JSON, blocks of text, or whatever. These days, JSON is probably the most popular queue message fodder, as it offers many of the benefits of semi-structured XML without the XML overhead. So queue mediation is not the solution to every problem, but it's a pretty good solution to quite a lot of problems. The pro is it decouples producers and consumers, and that the producers and consumers can scale separately. Queue mediated systems are typically tremendously resilient to outages, and it buffers the producers from the consumers so that consumers, if they were tightly coupled, you ran the risk of the consumer's being overwhelmed and messages being lost, but queues buffer the messages, allowing consumers to consume messages at their own pace. And because enterprise queuing systems typically have very long message retention in the queue, transitory outages or bursty behavior by enterprise systems typically does not overwhelm queue-mediated systems. So they're very, very stable. The con is that there is a certain amount of latency. No matter how efficient your consumers are in processing messages, there will be a little bit of latency. And if you have a scenario where that latency is important and your system is extremely sensitive to latency, queue mediation may not be the best pattern. Or if you do use it, you need to be sensitive to how quickly consumer side can scale up and process messages. And again, one of the things about queue-mediated systems that producers and consumers can scale independently. Another con is complexity, right? You need one more component, the queue, between the producer and the consumer. And as we've mentioned before, the properties on individual queues can make a tremendous difference to the behavior of the queue. And lastly, there's more configuration to manage. If you have a queue in your system, you have more configuration. So in Azure, queues and other resources are organized within a subscription into resource groups. And each resource group can have one or more namespaces. And of course, there can be one or more resource groups per subscription. And each namespace can have as many queues as the particular queuing engine allows. And this allows you to make well-organized, well-named queues that are relevant. So for example, you might choose to use resource groups to represent environments, dev, QA, pre-prod, and so on. Or you might decide to have resource groups represent major system divisions. So accounting versus payroll versus inventory. Namespaces are useful as well as they allow you to collect queues with similar functions into the same namespace. And so depending on your naming preferences, within a subscription, you can use any combination of resource group name, namespaces, and queue names to organize your queues. Basic vanilla queue in Azure is called a service bus queue. They're very high scale. A single service bus queue can handle millions of incoming messages an hour. They're very large and durable. They can have retentions that are measured in days, if not weeks. And they have any number of nice qualities that make them sort of the queue of choice for a nice vanilla queue. Service bus topics are a subset of service bus queue. And you can think about service bus topics, which are very useful queues indeed, as you can think of a topic queue as a queue of queues. In other words, there's one physical queue, but because of message properties, typically the topic name, on the topic queue, different consumers will consume different messages by using the appropriate filter. And in fact, the pub sub nature of queue consumers allows you to set it up so that consumer A is activated whenever a message with topic A enters the queue, and consumer B is activated whenever a message that has topic B enters the queue. And topic queues make dandy finite state machines. In other words, you can use topic queues and the topic names to represent the finite state of a message. So a message may come in, go through some initial processing, there's some decision made in the consumer, and then it's put back onto the same topic queue, but this time with a different topic that will be picked up by a different consumer, and so on, effectively implementing a finite state machine. Those of you who have done message processing using BizTalk will recognize this pattern immediately. The promoted properties in BizTalk can be used to decide which orchestrations will process a message. Event hubs are a special kind of very durable queue. If you have very, very high volume message situations like telemetry, event hubs are dandy. They're dandy for a bunch of reasons, but one of the things that makes event hubs truly useful is their ability to have partitions. You can think of partitions as being sub-queues within the event hub queue. And these partitions can either be assigned in a round robin if the producer doesn't specify which partition number is the target, or you can use partitions in the same way that you use topics by assigning particular messages to particular partitions, and then have different consumer groups target specific partition numbers, or all the partition numbers, depending on how you want to arrange things. This turns out to be extremely handy because you can use partitions in the same way that you use topics, or you can simply use partitions as a load balancing mechanism to be able to consume or ingest a large number of incoming messages. Again, very handy in telemetry situations. Event hubs have one more charming property, and that is the ability to have multiple consumer groups. And the rule is that every consumer group gets its own copy of the same message. So if I have a message A, and I have 3 consumer groups, each consumer group will get its own copy of the message. And you can think of the consumers of the consumer group as having their own cursor inside the event hub. In other words, consumer group 1 might act on messages extremely quickly versus consumer group 3, which takes a long time to act on the same message. And so you can think of consumer group 1 as remembering what its last message was, and consumer group 3 remembering what its last message was. And effectively, messages stay in the event hub until one of two things happens. Either all the consumer groups consume them, or the message times out. In other words, gets so old that it's thrown out of the event hub and into the dead letter queue. By the way, almost all enterprise queues have a dead letter queue. It's the places messages go if they don't get processed by the time their time expires. So here we have a really cool scenario. We have 3 consumer groups. One consumer group's job, provide to the message storage component a copy of the message that it's going to put into storage. Another consumer group is being used by Stream Analytics, which we'll talk about some more in future lectures, to produce KPIs, or that is to say this many over that many, or this many per that many type of measurements. And those things are being sent off to a dashboard. And then consumer group 3 is being eaten up by a logic app. Logic apps are the workflow mechanism in Azure. And the logic app is going to do some things to the message, do some processing, and then send it off to some other system. But each consumer group will get a copy of the same message. And because event hubs are guaranteed to deliver once and only once, no consumer group will get the same message twice. And assuming that each user of the consumer group can get around to processing the messages before they time out and go to the dead letter queue. Again, these things are measured in days or weeks, and so it would take something extraordinary to not be able to process the message. Each of the message streams, groups 1, 2, and 3, will get a shot at processing the same message. One other thing to note here is that enterprise queues typically have some sort of a system called a lease, which is to say, if, for example, the store the message process doesn't successfully process message number 47, what will happen is message number 47 will appear back in the list of messages for consumer group 1. It's called a lease. And as part of setting up your consumer groups and as part of writing a client that reads messages off the queue, you can specify how long the lease is. And so store the message might say, go get me the message at the beginning. And at the end, if it's successful, it would say, I've successfully processed this message. And then consumer group 1 knows that it can advance the cursor to the next message. If there are more than one store the message processes, leasing still works. Leasing works at the granularity of individual messages. So just know that leasing is a mechanism that you can leverage to return unprocessed messages to the queue on the occasion that the thing consuming the message doesn't successfully process it. Depending on the queue type in Azure, leasing may or may not be on by default, but leasing is an option on all of the message queue types. So here's a comparison of Azure queue types. And here we're going to compare storage queues, which we talked about last time as being part of the Azure storage mechanism, and service bus queues, which are a platform as a service enterprise queue up in the cloud. And you can see from the comparison that they have significantly different properties. And in fact, depending on the behavior that you want, storage queues or service bus queues, or one of the family of enterprise queues, may be a better choice for your use case. The important thing to think about, though, is think about what your use case is. Look at matrices like this one. There's a much bigger, more complicated one at the hyperlink that's below the table. And decide for yourself what queue behaviors, properties, sizes, and performance you need, and use that to determine what to do with your message. The other thing is that although most interfaces to things up in Azure are restive, know that some of the enterprise queues up in Azure offer the AMPQ protocol, which is a binary protocol, which is significantly more compact and faster than the equivalent restive protocol. You don't have to use AMPQ, but if you have devices out in the field and you're collecting telemetry from them, know that AMPQ might be an excellent protocol alternative, especially in high volume situations, or if you're talking to devices that don't really speak REST, they only speak AMPQ. Parenthetically, when they talk about FIFO behavior, first in, first out, they're only talking about it in terms of messages on the inside of a queue. The behavior of messages on the output side of a queue is something you need to control programmatically. So storage queues don't enforce FIFO for the same reason that the storage engine doesn't enforce FIFO, but you can turn that on for service bus queues if you want. There are pluses and minuses to enforcing first in, first out logic. But remember, that's only the order that things go into the queue. Whoever your consumers are may be consuming messages out of sequence in some circumstances. Other queue-like stuff. SQL Server has queues when it's installed infrastructure as a service. Just like you can say create table, you can say create queue. If you want to use SQL Server queues, you can, but there are lots of better enterprise queues available in the cloud. Service bus relays are managed under the queue umbrella, but they're not really queues. They're bidirectional mechanisms to poke messages through firewalls, and in the process, they buffer or queue the messages going back and forth. Azure IoT Hub is a sort of a queue, and in fact, it's bidirectional in the sense that it can buffer data coming from your devices and commands going to your devices. But unless you need the IoT features like device registration and bidirectional interaction with devices, probably want to think about using another enterprise queue instead. Securing queues. Most enterprise queues in Azure allow you to make a shared access signature policy. What that means is that you get a magic key, and that magic key is associated with either manage, send, or listen. Parenthetically, if you pick manage, you get send and listen. What this means, though, is that you can create a connection string to your queue that's only allowed to send messages, or only allowed to listen to messages, or can do all of the above. You can also use these policy keys to generate shared access signatures like we talked about when we talked about storage that can have shorter lifetimes and much more specificity. Here's a little example of creating a SAS token in code. I pulled this off of the docs at Microsoft.com and I annotated. Feel free to take a minute and stop the playback and you can see how it works. It's not terrifically complicated. It's about the same level of complexity as creating shared access signatures for storage. And they're used pretty much the same way. By the way, queues, functions, and logic apps absolutely live together. Queues are great glue. Almost every Azure component knows how to talk to a queue, even the analytic one. And functions in Azure, Lambdas in AWS, in other words, serverless computing things, have something called activation models. One of the activation models is, hey, a message has just showed up in my queue. And so you can write a little function that deals with the queue message and has all of the semantics you need without having to write a lot of other boilerplate. Serverless computing is not only new and cool, it's actually super useful. Likewise, logic apps, which you can use to make processing pipelines or graphs or complicated workflow scenarios, also can get initiated from queue activity. In other words, the workflow can wake up and put the message through the workflow when it sees a new message on the queue. Here's a couple of queued workflow examples. There are two fundamental patterns. One is hub and spoke. If you're a BizTalk person, hub and spoke looks pretty familiar, with the queue in the middle being a message box. These are an excellent example of finite state machines. And of course, the traditional workflows. Here we have a workflow that's got a couple of queues mediating the different steps. But either way, queues are terrifically useful. Here's how you can mix and match one of the most important enterprise patterns, CQRS, with queues. This is an actual example for a high-scale e-commerce website. And the challenge the developers had was that there were hundreds of millions of different parts, SKUs, and most of the website requests were to search these parts or pull up information about a particular part. So on the read side, on the top, what we did is we built a little widget. We treated the database like a queue, and using an Azure function, we listened for changes in the Azure database and made a static representation of the part. So its block of information, its price, the quantity, all that other good stuff, links to pictures and all those things, and then push those into a Redis cache. By the way, on the front end, we also used an enterprise edge cache, in this case, Akamai. But you can see how we're buffering some of the read output. The other thing that happened was, of course, people would cart up parts and want to check out. And so we had a processing pipeline. And as the writes, the changes to the cart or converting a cart to an order or letting the customer know about the order status or whatever was done, we used a topic queue to keep track of all those things. And depending on the topic, it activated different parts of a processing pipeline using a very finite state machine sort of way. And one of the messages that could occur in a topic queue was a notification, which would cause notifications to pop up on the website. So here's sort of a hybrid of using a queue, workflows, caching, functions, databases, and a website to implement a CQRS pattern. APIs. Like we said, most Azure things expose a REST API. And like we said before, most of these APIs have a nice facade built in. So there are Queue libraries for .NET, Java, JavaScript, Ruby, Python, and pretty much anything else you can think of. Node, if it runs in the cloud, anywhere on the Azure platform, or runs on the prem in any kind of language whatsoever, you can pretty much get to your Azure Queues. And the very worst case is if your programming language doesn't have a library available, but it is capable of making an HTTPS call, you can go against the REST API. And for the most part, these are pretty easy to understand. Azure Service Bus Explorer is a dandy tool, a freebie from Microsoft that you can download and allows you to look at the data in queues, particularly helpful for developers, but also for ops folks that are trying to figure out why messages aren't going where they're supposed to be going. Parenthetically, enterprise queues up in Azure have gotten an API facelift and now support a non-locking peak operation so that if you want to, you can use the API and write your own queue monitoring or queue notification system without worrying that your monitoring or notification engine is going to cause locks inside the queue. And lastly, Azure Application Insights and Azure Monitoring give you good information about queues, and they help you manage them, including giving useful advice.